Hey everyone, it's Mr. Boltri here bringing you a video where we're going to talk about vectors. So in order to do that, first we're going to introduce vectors, then we're going to talk about vector addition, and then talk about why one of the ways in which vectors are useful, which is to talk about projectiles. So first, what is a vector? So to talk about what is a vector, we'll first talk about what is not a vector. So a scalar is not a vector. Scalars show only magnitude, like the number of marbles or the amount in my bank account. And then a vector shows the magnitude and the direction. When we talk about direction, we mean like a physical direction, like northeast, southwest, up, down, left, right. So money in my bank account, even though my bank account can be negative if I'm in debt, it wouldn't make sense to say the negative stands for south or west. I don't have south. I don't have $20 south. I just have negative $20. But where the negative in a vector means actually south or west or left or down or whatever we want it to mean. So here we have showing vector notation. This is a velocity vector. And honestly, whenever we write a vector, we should put the arrow above it. I've been a little bit lazy about that. I'll try to be better, but vectors are denoted by the arrow above them. So this is 20 meters per second north, and that north is the direction, which is why velocity is a vector. Speed is a scalar because we don't care about the direction. So that's kind of the classic definition of what is a vector. So here's just kind of some vector notation. So if you have 20 meters per second north, you can write that one of, well, three ways, basically. You could write it out, 20 meters per second north, or you could say 0, 20, 0 in the kind of pointy parentheses brackets thing. And what this means is it means 0 meters per second in the horizontal x direction, 20 meters per second in the vertical y direction, and 0 meters per second in the z direction. And I've not seen very many problems so far that have objects moving towards or away from you, but I'm going to teach it to you now just because I know it will come up later when we start talking about like rotational stuff. So this is the x, y, and z direction. That's one way to write it. And another way to write it is you could use the I hat, j hat, and k hat notation, which you'll see on the AP exam. I prefer this top one because I think it's just easier to look at and read, but I know the AP exam can sometimes use this I hat, j hat, and k hat notation. And just I, j, and k just mean x, y, and z, but they chose different letters for, I'm sure, reasons that are good and make scientific sense. That's if something's going straight up. If it's going like, I don't know, down and to the right, we're going to have a portion of the vector that is to the right, 6, portion of the vector that is down, negative 18. And these are called kind of the components of the vector, the horizontal component, the vertical component, where component is a word that means piece or part. And you can write that 6 in the I direction, that's the X horizontal direction, negative 18 in the Y direction, that's 18 down, and 0 in the K direction, it's not coming towards you or going away from you. So it's a little bit about vector notation. Now let's talk about vector addition. If we were to take those two vectors and add them together, what do you think it would look like? Well, we go up for quite a way. Let's talk about displacement just because velocity gets a little bit tricky because you have to then multiply by time. But you go up 20 meters and then down and to the right, down 18 meters and to the right 6 meters. So I think hopefully it's pretty obvious that you, all in all, total, traveled 6 meters to the right and 2 meters up. So it's going to look like that. And this is just called tip to tail or tail to tip addition, because you just take one of the vectors and you put the tail on the tip and then you add them just like that. And you can add the x components, the y components, and the z components just straight down like that. But things get more complicated if you're given a problem that looks a little bit more like this. And problems that look like this are, unfortunately, a little bit more common. So if you travel 20 meters north and then 19 meters kind of east and south, a little bit east of south, you're going mostly south and a little 30 degrees east. What does that look like? So whenever you see a problem like this, the first thing you're going to want to do is make a diagram. So first you go north, then you go a little bit east, and it's asking me for the total displacement. Then, just to make it easier on yourself, you're going to try to rewrite the problem in terms of vector notation. So 20 meters north is really easy, 0, 20, 0. And then 19 meters kind of south-ish, east-ish south, we're gonna wanna draw a picture just for that too. So here I have south, and 30 degrees east of south, we are going to be trying to figure out the horizontal and vertical components of that. So I'm not going to take you through the trig because I know you know SOHCAHTOA, sine, opposite hypotenuse. You can draw your triangle here and you can figure out using SOHCAHTOA the horizontal and vertical components of that vector. And then you can rewrite it like that and then just use tip to tail addition and get back to your answer. Now, normally this would be a fine place to stop, except if it's on a multiple choice question, you're probably 6, 2, 0 is probably not going to be one of the answer options if the question was written as 20 meters north, 19 meters southeast-ish. So you're going to have to try to figure out what is the magnitude of the vector, and then you can just use Pythagorean theorem because we have the horizontal and vertical components. A squared plus b squared equals c squared. You should be good on that. And then you can just figure out the angle, this time using tangent, because we know the opposite and adjacent. So we can find it's 6.324 meters, 18.4 degrees north of east. And that's kind of your basic vector problem. It can get more complicated from there, but that's kind of one that I've seen kind of pretty commonly on multiple choice questions and stuff like that. So now let's talk about one of the ways that we can use vectors, which is when we're talking about projectiles. So a projectile is just kind of anything flying through the air. And specifically in this course, it's mostly going to be a word that we use specifically for things that are subject only to the force of gravity. So with examples of projectiles, we can ignore air resistance unless we are specifically told that we cannot ignore air resistance. So the only force acting on a projectile is going to be gravity, which gives us this very interesting coincidence or just fact, is that the acceleration of a projectile in the horizontal direction, it just keeps moving with a constant velocity. In the vertical direction, it is being pulled down by gravity, and it's obviously not accelerating towards or away from you. So what we can do from that is, this is kind of the classic setup, is if we're told that something is launched with an initial velocity kind of up and at an angle. So then what can we do with that problem? Well, first thing we're going to want to do is we're going to break it into its component vectors. We want to know how much of that up and to the right is in the horizontal direction and how much of it is in the vertical direction. And once we get our kind of component vector, we know that it's moving, it has an initial horizontal velocity of 17, initial vertical velocity of 36. Then we can see how these velocities change with respect to time, because the acceleration, then the horizontal velocity is just going to be 17 the whole time. But the vertical velocity is going to be 36, and then a second later it's going to be 26, 16. And so we can look at what happens with the graphs and how they move from there. So this has been kind of a pretty quick, short introductory video on vectors. We'll do some practice problems, but really the most important thing here is we're setting up our ability to solve those complicated projectiles problems. So let me know if you do have any questions, and I'll see you in class. Go Bears.